Sequences in infinite series, an overview, part 1. A sequence is an ordered list of numbers. A sequence may be generated by a recurrence relation or by an explicit formula. For example, the sequence 3, 6, 12, 24 can be defined by the explicit formula a sub n equals 3 times n. So the nth term is equal to 3 times whatever n is. It can also be defined by the recurrence formula a sub 1 equals 3, a sub n equals a sub n minus 1 plus 3. Now, this notation takes a little getting used to. The first term in a recurrence formula is given. Now, let's say we want to find a sub 2. To find a sub 2, we look at a sub 1. And then to the term a sub 1, we add 3. So what is a sub 1? A sub 1 is equal to 3. And so a sub 2 is 3 plus 3, or 6. To find a sub 3, we look at a sub 2 and add 3. So what's a sub 2? A sub 2 is 6, and 6 plus 3 is 9. To find a sub 4, we look at a sub 3 and add 3. A sub 3 is equal to 9. 9 plus 3 equals 12. And in general, to find a sub n, we look at the previous term, a sub n minus 1. And to that previous term, we add 3. Let's look at an explicit formula for a sequence. Let's find the first 4 terms of this sequence. If n equals 1, the term is 1/2. If n equals 2, the term is 1/4. If n equals 3, the term is 1/8. And if n equals 4, the term is 1/16. When we go to graph the terms, we put n on the horizontal axis and the a sub n on the vertical axis. We don't connect the dot. With a sequence, you just put in the terms, and for each term you put exactly 1 dot. Notice if we graph this sequence, we can see geographically, geometrically, that the sequence is getting closer and closer to the n-axis, and that's in keeping with it looks like the sequence is getting closer and closer to 0. Let's use the explicit formula to find the first 4 terms of this sequence. This one's a little more complicated. So first, if n equals 1, what will you get? Every time you see an n, put in 1. Okay, so every time we see n, instead of n, we replace n with a 1. And when we're all done, we get negative 1/2. Try n equals 2. See if you can do that. For n equals 2, I get positive 2/5. Now try n equals 3. For n equals 3, I get negative 3/10. Let's try it one more time. Try n equals 4. If n equals 4, I get 4/17. Now let's go ahead and graph this like we did the other sequence. What is the graph of this going to look like? Again, Remember, we don't connect the dots. We just put one dot in for each term of the sequence. So notice that a sub 1 is below the axes, a sub 2 is above it, a sub 3 is below, a sub 4 above, a sub 5 below, a sub 6 above. So it goes back and forth, back and forth, back and forth. And when that happens, you have what's called an oscillating sequence. Now let's look at a recursive formula. This is one of my favorite sequences. And it can be done explicitly. The explicit formula is pretty complicated. The recursive formula for this particular sequence is actually much easier. So we want to find the first 8 terms. We've already found the first 2 terms. A sub 1 is equal to 1 and a sub 2 is equal to 2. That is given. All right, now what would a sub 3 be? So look at your formula. A sub 3 would have to be, let's see, if n equals 3, then n minus 2, let's see, that would be 1, and n minus 1, that would be 3 minus 1, that would be 2. All right, so a sub 3 is equal to a sub 1 plus a sub 2, which is equal to 2. Likewise, a sub 4 would have to be a sub 2 plus a sub 3. Do you get the hang of it? To find a sub 5, you're really just adding the 2 previous terms. To find a sub 6, add the 2 previous terms. A sub 7, add the 2 previous terms. A sub 8, add the 2 previous terms. And you might be recognizing this sequence at this point. You have what's called the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, and the next one would be 13 plus 21, or what would that be? 34, right? All right, so I'll see you again in part 2 of this section. Take care and have a great day.